school due end of the week, so please do PS4, okay? Alright, don't come tomorrow, okay? If you come tomorrow to the lecture, you might find it's completely empty and then you're the only one here, alright? So don't come tomorrow. So someone asked me last week, and I promised to get back to you about the multiplication method. So why do we do this? Why do we take the top L bits of the lower half compared to just taking these instead? Right? Why do we need to take this? Why don't we just take this? Why don't we just shift it right away from here instead of doing this mod and then the shift? So the answer is because the bottom bits are actually less informative. So as a rule of thumb, in hashing, you want to use all the information you have in the key.
Idea is so bright.
Okay. You might want to pay attention, it might come out exam. Okay, so as a rule of thumb, you want to use all the information in the key. Alright, so when you multiply A times K, the bottom bits at least actually contain less information on the key. Here's some examples. So if you multiply these two binary numbers together, what you will notice is that these digits actually contain information in these bits only, right? Which is not great because we're not incorporating all the information that we want in the key. All right. So here's a bigger example. You can read more about multiplication over here. Okay. So that's why we are not just in this slide. We are taking this part of the top half. Of the bottom half. So the top part of the bottom half, rather than the bottom half. All right. So that's the answer to that question. Any questions? Or I don't have this on the thing. This live presentation. You're doing so well. Give me a second. Up.
Dokter saya kan aku exam.
Okay, so full screen. All right. So if you thank you. Orders to get well. All right. Any questions? If you have any questions about administrative issues or a question, please put it up. Yeah. Okay. So let's get on with today's material. So today's material, we're going to be looking at MSTs. Okay, so by the end of today's session, you should be able to tell me what an MST is and what is its key properties. And then we'll talk about Prim's algorithm and running time. Okay, so what is Prim's algorithm? Allows you to find the minimum spanning tree. Okay, so let's look at this. So why are we concerned with MSTs? So here's a sample problem. We start with sample problems. So imagine you have this fictional country, Singaporea, who has recently rolled out wireless power towers. So this is actually something in development nowadays. Instead of having all these cables providing power, you can have wireless power, which is something Tesla experimented with years ago. All right. So, but the problem is that connecting up these transmission towers is not exactly easy. You have to beam the tower from one to the other, and then there's some cost involved there. And so you are hired to find out how to connect up the towers to minimize the cost. Okay. So let's imagine that you have this following graph. Right. This is the following graph. Again, it's a single graph, and it's undirected. Okay, it's undirected. So what is a spanning tree? Let's define it. A spanning tree is an acyclic subset of the edges that connects all nodes. Alright, so it's very simple. It just means that it's a subset of edges such that all the nodes are connected. So from one node you can go to any other node in this spanning tree. Okay, so that's the idea of the spanning tree. The weight of this spanning tree is simply the sum of the weights of all the edges in the tree. Okay, it's the sum of all the weights along the edges in this tree. Right, so the weights in this tree will be 32. Now what we want is usually a minimum spanning tree, and the minimum spanning tree is a spanning tree with the minimum weight. Right, so if you sum up all the weights, right, along the edges in the spanning tree, that should give you the minimum weight among all the spanning trees that you can construct from this graph. So for example, this is one spanning tree, the weight is 32. This is another spanning tree, this is the minimum one, it has weight 20. Alright, so when we want to find the minimum spanning tree, this is what we want. So imagine as though each of these numbers, these weights, represent some cost, and you want to minimize the total cost. Alright, so that's the intuitive meaning of this. So here's a question. Let's do this quickly. Can we use the MST to find shortest paths? Alright, so remember we talked about shortest paths last week. Can we use MST to find shortest paths? So how many people think yes, we can use MST to find shortest paths? Okay. Only on connected graphs? Only on dense graphs? D, nope. Okay, and E, I'm not sure. Alright, so it turns out that this is a very common error, that shortest paths are not equivalent to MSTs. Okay, so when you're looking at a problem that is asking you to connect stuff up, minimizing total cost, that's minimum spanning tree kind of problem. Alright, but if you're asking the problem asks you to find shortest paths, that's the shortest. That's the shortest path. You get from one point to another by minimizing the distance. That's the shortest paths. So these are different problems. You can see this here. This is your minimum spanning tree. All right. The shortest path from S to D is this edge here. This edge is not in the minimum spanning tree. Okay. This edge is not in the minimum spanning tree. So be careful. Right. Be careful. This is a very common mistake. I've seen it year on year. Right. So it's making a mistake that they confuse the shortest path with minimum spanning tree. Okay. So there's a shortest path tree. There's a minimum spanning tree. They are different things. Okay, so you keep that separate in your head. So MST is not the same as shortest path. Alright, MST has many applications, just like shortest path. You can do it for network design, telephone networks, electrical networks, computer networks. You can imagine, right, in a lot of these situations, you would like to construct, right, a tree, like how to connect them up together by minimizing some cost. Right, so there are a lot of different applications for this. It's also used in medical image processing. So this is a paper, right, where they have used MSTs in order to get the arrangement of nuclei, okay, for cancer research. This is an example in machine learning, pattern recognition. So they want to find the manifold of basically, if you have this kind of data points, like this spiral structure, you want to find basically connect up the dots, right? So they form a kind of like a manifold, a plane that needs to work. Okay. It's also used for anomaly detection. So for example, if you have data points representing events, you can cluster them together, and then you can build a minimum spanning tree between the clusters, and you can look at the MST that is the longest edge, the longest edge in the MST, and then you can see that, oh, maybe this cluster is an anomalous cluster. It's very far from everything else. Okay? So MSTs have a lot of different applications. So we're going to we'll start out with some basic properties of MSTs. Why are we looking at the basic properties of MSTs? Because they're going to lead us to an algorithm. Okay? We look at the basic properties, and then from the properties, we will find a very simple algorithm. Okay? So let's start off with some simplifying assumptions. I'm going to say edge weights are distinct. Right? You have no duplicate edge weights. Right? Make things simple. Okay? I'm going to consider duplicate edge weights, and that the graph is connected and undirected. Okay? So let's start off. The first property is that there are no cycles in our MST. Right? It's called a tree anyway, so there shouldn't be any cycles. So the first property is that there is no cycle. Why is there no cycle? Well, it's very easy. If there was a cycle, we can just remove one edge, and that will reduce the weight, but the tree will remain connected. So we don't have to worry about that. Okay? So we have the cycles. What happens if you cut the MST into two parts? Okay, so I have this MST. The MST is the one shown in red. Okay? And I cut this edge. So I remove that edge. What happens? What do you think happens when I do that? What can you say about this part and this part?
Connected component.
What do you think? So if I have this MST, I remove this edge. What is this part? Is this part a full graph, or is it a star? Is it a line? Or is it a, what do you think it is?
Connected component.
It turns out that if you cut MST into two, you get two MSTs. Okay, graph T1 and graph T2 are also MSTs. Alright, so you cut MST, you get two MSTs. Right, that's a nice property. So if you cut MST, the two pieces are both MSTs, that's property number 2. Now let's look at property number 3. Property number 3 says it's called the cycle property. It says that for every cycle in the original graph, the maximum edge is not in MST. Right? So why is this the case? So imagine that this is the maximum edge on a cycle. Right? So assume that the heavy edge is in the MST. Okay, so this is the heavy edge. All right. So removing this max weight edge cuts the graph into two. And now I can just add this other cycle edge, right, which is not in the MST, that crosses this cut. Right? Now, this new MST has less weight. So the initial MST cannot be an MST, right? It's contradiction. So let's repeat that again. I start off by saying that, okay, assume that I give you an MST, okay, I give you an MST, and I say that, oh, the heavy weight on the cycle is in this MST. Alright, I'm going to show that this leads to a contradiction. Right? So what I'm going to do is I'm going to remove this this weight. I'm going to remove this edge. Okay? And I'm going to add the other edge on the cycle. Right? This cycle on the edge is of less weight than this because this is the max weight. Right? So I'm going to remove that. And it turns out that now, look what happens. I will have an MST still, but the MST is of lower weight. Right? So this means that the initial assumption that the initial MST is not true. It cannot be minimum because I've just constructed a new minimum spanning tree by removing an edge and adding on it. Okay? So the point is that the graph cannot be an MST with a max wedge edge along a cycle. So again, remember property 3, cycle property. For every cycle, the maximum edge is not in the MST. So here's a question. All right, let's put this on hold everywhere. So we talked about the maximum weight edge in a cycle. How about the minimum? For every cycle, the minimum weight edge is always in MST. Is that true, false, or something in the middle? Okay, so let's do. Okay, so try to think about this. I will leave this here. All right. So I'll give you 30 seconds, and you try to figure it out. Talk to your friend. And then let's see. I'll give you 30 seconds. Talk to your friend and put in your answer. All right. So think carefully. Do you think that the minimum weight edge must always be in the MST for every cycle? Is it true, false, or is it I don't know? Let's have a look. So 13 responses, 31% said true, 54% said false, and 14% said this. By the way, you guys laugh, right? But this somebody actually put this in an exam once for the final, and then don't do this, please. It's automatic like wrong. Okay, it's automatically wrong. So don't do that. Okay, so it looks like we're even. Okay, like people think that it's true or false with someone even. Let's look at the answer. So the answer is false. Okay, the answer is false. The minimum weight edge is not always in the MST. Alright? It may or may not be in the MST. Here's an example, a counter example. So this is the MST, alright, in black. Alright? And this 7, okay, this 7 is actually the minimum weight edge along this cycle and on this cycle. And you notice that 7 is actually not in the minimum spanning tree. Okay, so the minimum weight edge on a cycle not necessarily is in MST. Now, we know that the maximum weight cannot be in, but it's not necessarily that the minimum weight is inside. Okay, so those don't be tricked here. Okay. All right. So property 4 is called the cut property. Pay attention now. The cut property turns out to be going to be the important one for today. All right. The cut property says that for every partition of nodes, the minimum weight across the cut is in the MST. Okay, so let's break this apart and try to understand what this property says. Alright? So this is the main edge of the cut, but what is a cut? Alright? A cut in the graph is simply a partition of the vertices into two disjoint subsets. What this means is that I take my nodes, okay, intuitively, and I put one node in one part and one node in the other. Okay? So there are no overlapping nodes in these two sets. Okay, they are disjoint. Alright, took some nodes, I put it in one place, take their nodes, I put it in another place in these two sets. Okay, and there are some edges that cross this cut, right? They connect nodes in this set to this set. So these are the edges that cross the cut, right? So let's recap. A cut is when I take the nodes and I just split them into two subsets. Okay, and there's disjoint, so there are no overlapping nodes there are no nodes in both subsets. Okay, and then I look at the edges that cross this cut. Now, if I look at the edges that cross this cut, what the cut property says is that among all these edges, the one with the minimum weight must be in the MST. Okay, so that's what the cut property says. So the proof is by contradiction, alright, so it's quite simple. So imagine that this is the mid-weight edge on the cut, but we didn't include it in the MST. Okay, we didn't include it in MST. Instead, we've included some other edge E prime here. So what we're going to do is we're going to just remove this guy and add this one. And then what will happen is that we will have a new MST with lower weight, right? Because this is the mid-weight edge on the cut. This one had something larger, we just remove it, put this inside, and now we have a lower weight MST. So contradiction because the initial weight could not form a minimum span tree. Okay, so it's by contradiction. Okay, so remember this. The proof is there, but it's very important to remember the property. Okay, the property is quite intuitive actually. It says that look, if you put it to two disjoint subsets, the minimum weight edge must be in the MST. Okay, minimum weight edge across the cut. So let's test your understanding. Let's try this. For every vertex, the minimum incident to outgoing edge, let's do incident, alright, because there's no direction here, is always part of the MST. Is this true, false, or we are unable to determine? Alright, so let's again chat to your friend and let's see. Okay, I'll put this back. Okay. So for every vertex, the minimum incident edge is always part of the MST. Is this true or not? Okay, I'll give you a minute. Check with your friend. Try to think it through. Okay, time's up. Let's have a look at the solution. All right, we have 14 responses. 15 solutions in. So about 57-60% think it's true, 40-something% think it's false. So about fairly even, given 14 responses. Let's have a look. So the right answer is that it must be true. Why is it true? It's true because of property 4. Right, so property 4 is the one you want to pay attention to. What does it say? The cut property says that for every partition of nodes, the minimum weight edge across the cut must be in the MST. One possible partition of the nodes is where one node is in one set on its own and all the other nodes are in the other set. Right? So that means all the outgoing edges form the edges across the cut. And the minimum edge must be in the MST, hence for every vertex, the minimum incident edge must be part of the MST. Okay? So it's not just enough that you kind of memorize the properties. You must know the implications of the properties. Okay, and then from there, then you can derive so that's why it's very important to have this all integrated together. This is another example. Okay, so again, if you just split one node on its own, again, this is one cut, this one subset, this is another subset, and then the minimum one should be in MST here. Here is one. All right. Okay, so let's try this again. For every vertex, the maximum incident edge is never part of the MST. So how many people think it's true? And you're not tricking me again. False, or I don't know. Right? So let's. Oops. Where is that? So have a look. So just now we talked about the minimum edge, right, on a vertex. How about the maximum of the vertex?
If you only got one vertex, it's never one edge. You can never with maximum. I think it's like that. One edge.
Let's do it quickly.
Where?
Right. Just try to get 20 points. 30 responses.
Wow, you're too close, yeah. Cough so long already.
Okay, so 3 more. Okay, results 17, 18. 2 more.
Faster,
2 more.
go and vote, 2 more, Number 11. Yeah, go and vote.
20. Okay, so most of you think false. Okay,
Oh, next one.
a few people are not sure. So that's okay. Let's have a look. The right answer is false. Okay, why false? Is because some edges can be a minimum to one node, but a maximum to another. Right, and if the minimum edge is always in the MST, then the maximum edge for a particular node can be on the MST. Alright, so please keep this in mind. Alright, that the maximum edge can be part of the MST. Alright, that minimum edge must be part of the minimum incident edge on every node must be part of the MST.
Oh, yes,
the maximum edge can be part of the MST as well. Alright. Okay, so yeah. Alright. So remember the 4 properties. Okay, the 4 properties. Number 1, no cycles. Okay. 2, if you cut an MST, the 2 pieces are also both MSTs. The cycle property says that for every cycle, the maximum weight edge is not in the MST. And the cut property says that for every cut, the minimum weight edge that crosses the cut must be in the MST. Alright? Today, I would say this one is the important one. Okay? Cut property. Let's see why. Let's start with Prim's algorithm. Alright, next week we'll cover Pascal's, but today we'll do Prim's. So Prim's algorithm wasn't invented by Prim's, as you guys know already, right? It's an example of the Stigler's law again. But it was initially invented by Jarnik back in 1930. Prim rediscovered it in 1957, and then Dijkstra rediscovered it again in 1959. Okay, so it was discovered by 3 different people. Again, it's not named after the original inventor, it's named after Prim. Okay, so what's the basic idea? The basic idea is really, really simple once you know the cut property. Alright? So here's the basic idea. Imagine that you have start off with a set S of the nodes. Alright? Of a connected set of nodes S. Okay? Initially you just put one of the nodes into S. Okay, just pick one. Pick any of the nodes and put it into S. Alright? So I'm going to identify a cut. Alright, the cut is this. The cut is either S and everything outside, everything that's not in S. Alright, so I took S equals to A, so this is one cut, and the other cut is everything else. Okay, this is everything else. Alright, now what does the cut property tell me? What does the cut property tell me? Yeah, so the cut property tells me that the minimum outgoing edge must be in the MST. Right? So you know that 3 must be in the MST, right? You know this. So what we're going to do is we're going to find the minimum weight edge on the cut, alright? And then we're going to add the new node to our MST. In this case, it's G. Alright? G is going to be added to our MST. So that's essentially the basic idea. Alright, we're just going to repeat this process again and again. We're going to add some node to A. We're going to identify some cut. We're going to find the minimum weight edge across the cut. Alright, in this case, once we add G, the number of edges has grown here, right? And now we have to identify among these, right, which one is the minimum, and then we add a new node to S. Okay, so we repeat this process again and again. Okay, so in this case, if you look at these edges, right, the minimum one is 4, so we're going to add D. right? Here, once you add D, then these are going to be your edges across the cut, right? So you can, if you want to visualize it a bit better, you can map this graph to look like this. You can see that there is an set S here, right, consisting of nodes that I've already added into my minimum spanning tree, and these are all the nodes that still I haven't added yet, okay, yet to be added to my MST, right? So when I see this, it's very simple. I know that the minimum of these must be my MST, so I just keep picking the minimum, right? So very straightforward. First algorithm is very straightforward. So here's a quick question. You guys should know this. This is a giveaway, right? So how do we find the lightest edge, the one with the minimum weight on a cut? Do you use a priority queue? How many people think we use a priority queue? Okay.
Priority queue, priority queue.
DFS or DFS?
Priority.
Dijkstra. Let's go use Dijkstra. It's not correct. And E, I don't know.
Priority queue.
The right answer, of course, is priority queue. Remember, priority queues let us find the minimum or maximum very quickly, right? Depending on what you want. Whether you use implemented minimum or maximum or AVL, it allows you to find these things. So we want to use a priority queue. Okay, so let's go through an example. Okay, let's go through an example here. So let's just say I add D. Okay, D is the first node in my MST. And look here, these are my outgoing, these are my incident edges. Now, which edge should I pick? 4. Good. So among these, I pick 4, and then I add G. So what's going to happen next is that once I see add G, right, I need to check all the outgoing edges again, right? So what's going to happen is that I'm going to, when I add G, I'm going to do some updates. Okay, right? So each one of them, I have to update essentially my connection to the next node. Right? So for example, E here, when I was only having D, to connect to E, I need to do 16, right? But once I add G, the connection has to be updated, right? The minimum edge to G is no longer 16, it's 6, right? So I need to update my priority queue. Okay, I need to update the key in my priority queue. It's the same here for H, right? So if you look, H originally was 9, but the moment I add G, I need to update that to 8, all right? So instead of storing so many edges, I'm going to store the minimum ones among the connections, right, to across the cut. Okay. Again, I'm going to repeat the process. Once I update my priority queue, I'm going to add A, right? So A is the smallest one now, 3, of course. I'm going to take that out, and then I'm going to update my edges and add new ones if necessary. Okay. So in this case, I'm going to add C, right? C was not previously, so I'm going to add C. 15, and then I'm going to update this H to 3, right? To 5, sorry, to 5. Okay, and then I repeat this process. I keep going on and on and on, right? It's quite straightforward. We just keep adding new nodes, and whenever I add a new node, I need to update the weights, right? Already in my priority queue, and then I keep doing that until I'm done. Okay, so there you go. You're done. You're finished. You have your minimum spanning tree. Okay, so everyone followed the procedure. It's quite straightforward. What we're doing is we take out a node, right, the one with the minimum weight, right, and then once we add it in, we look at the weights across the cut, right, and because sometimes we are adding an edge, which is something with a minimum weight to a particular node, we don't store actually all the weights, all the edges. What we're storing are the target nodes, right? Because we're storing the target nodes, we need to update the weights if necessary. Okay, if there's a smaller edge that connects to that node, we need to update the weight of that node, right? Okay, so that's the idea. All right, so that's Prim's algorithm. Essentially, it works because of the cut property, right? Each edge that we add is the lightest on some cut, so every edge is on the MST, and then we're done. This is very simple, right? Because of the cut property. So what is the running time of Prim's algorithm?
I think B.
So what's the running time? Let's have a look. Put your answer onto go everywhere. All right. Here's an exercise in figuring out the running time. Okay, it's either OB, OE, OE log B, OB log E, OEB, or B log B. Okay. So try to figure this out. You are using a priority queue here. Alright, remember that
V log E.
Remember the operations that you
V log E,
deploy
baby.
when you are adding
V log E, baby.
your MST. So you need to remove a node, you need to add a node to your MST, and after you add the node to your MST, you need to update your priority queue. So think about the operation that you need to update your priority queue.
Well, coming.
So I'll leave the pseudocode up there, you can see. Okay, I'll give it a minute. Again, try to break it down, look at the steps. And for each step, see how many times you repeat that. And try to find out the cost.
V square. OV square.
Okay, let's have a look. We have 16 responses so far. Seems quite across the board. We have the maximum is V log E. We have some people saying E log V. And a few people saying E log E, EV, and so on and so forth. Okay? So let's look at the answer, guys. Let's look at the answer. So if you answered E log V, you're right.
Wow. 不可能.
So this is. So the question is why? Why is this E log V? Right? Why is this E log V? So let's do the analysis. Right? Let's do the analysis. So each vertex, right, is added or removed once for the priority queue. Right? This is done only once.
V log V.
Right? So it's V log V. That part. Correct? It's V log V. But each edge that you examine, right, can cause a decreased key. Right? Remember that we were looking at the nodes in there. It can cause a decreased key. How many nodes do you have in a priority queue at worst? V, right? So for each edge, you cause one decreased key, that's E times log V. Alright? So in total, you get E log V. Right? So that's one. Okay, so the answer to this one is E log V. Right? Okay. So E log V, Prim's algorithm, right? Remember what the basic idea was? The basic idea is that we maintain some set of visitor nodes. We gradiently grow it, right? By adding a node that is connected via the lightest edge. Right? And we're going to use a priority queue to order nodes by edge weight. Alright, that's the idea. Now remember Dijkstra. What do we do with Dijkstra? Dijkstra, we maintain a set of visitor nodes. We again gradiently grow the set by adding the neighbor node that is the closest to the source. Right? Closest to source by looking at your distance estimates. Alright? Again, we're using a priority queue. Right? But the priority queue now is ordering the nodes by distance, not by edge weight like in Prim. Okay? So you see that the structure, both of them are greedy algorithms. Okay? They are both efficient and optimal. They are also both efficient and optimal because they leverage on some optimal substructure, actually. Okay? What is the optimal substructure in Prim's algorithm case? Right? Remember when we cut the MST, we get two optimal MSTs, and then now that we know that every edge that crosses the cut, the minimum one must be in the MST. Right? So essentially, both of them leverage upon Dijkstra, however, uses the optimal subpath property. Right? So both of them leverage optimal substructure in order to build up their solutions. Okay? They build up their global solution from simpler subproblems. Alright, so we're done with this problem actually. It's very simple. If you were actually hired to do this job, right, all you need to do is model the problem of the graph. So you model like all the little like transmission powers as nodes, right? And then you just for each outgoing node, right, you just have an edge to all the other nodes with some cost, and then you construct the minimum spanning tree, and then you're done, right? Just run prims algorithm, all right? And then you're done in elongate time, right? So that's it. That's minimum spanning trees. Next week we'll be talking about Kruskal algorithm, algorithm as well as variations, but that's next week, okay? So today you know about minimum spanning trees, and you know what the properties, okay? And the difference between prims and similarities actually between prims and Dijkstra's algorithm. So let's do some questions now before we go to problems. So do we have any questions? No, Prince was easy. That's good. Okay, so if there are no questions, okay, let's get well. Thank you. I will get well. I will get well. Okay, so if there are no questions, I have questions. So before questions, next week please revise Kruskal algorithm and the union find data structure. Next week we'll be talking about union find. It's very useful data structure, and it's good that you revise it before you come to class. Okay. All right. So I have questions, and so some students have asked me to provide some examples on problem solving in class. So that's what we're going to do. All right. We're going to talk about the first problem is like a warm up. Okay. It's our longest path in a DAG. Right. I told you I'll talk about it last week. I didn't get to it, so today we'll talk about it. So longest path in a DAG. So what's the problem that we're talking about? I give you a DAG. I give you a directed acyclic graph. I want you to tell me what the longest path is, i.e. the simple path with the maximum weight. Okay, the simple path with the maximum weight. So remember what a simple path is? A simple path is that there has no repeated edges or no repeated vertices. Okay, zero, right? So you have no cycles, essentially, no cycles. Okay, so that's your simple path. Can you find the longest path in a DAG? All right. So in this example, this is the longest path. Okay. Let's say from S to this point, all right? So the question is, can you find longest paths in a DAG? So that's your task. Why don't I give you a bit of time to do it? Let's say 3 minutes, all right? You don't need more time, I'll give you more time. But 3 minutes, okay? I'll work together, and then after that we'll come over how to think about this problem and how to find a solution, okay? Let me tell you in advance that there are two simple, straightforward solutions to this, all right? Two straightforward given what you already know. Alright, so try to figure it out and leverage what you already know. That's the hint. So everybody clear on what the problem is, right? It's give a DAG, it's a directed acyclic graph. Tell me what's the longest path in the DAG. For those of you who come up with a solution, try to prove to yourself it works. Okay?
I find the longest path in the DAG. Reverse Dijkstra.
Yeah, that's
No. You need to find the longest path. Yeah, reverse Dijkstra right there. No, but you need to do it on all edges. You need to Dijkstra on all edges. You need to Dijkstra on all nodes. Dijkstra carrying a very soft Like, see the universal, I told you don't know what you saw. You don't know what you saw. Oh, you never had the door. The ball here, there.
So in this case, I want the longest possible start starting from some source.
And then you actually can find all these. You can find a bigger figure of all these. diagram of one ball, and then you already get all the value of all the weight. Does it make sense? Reverse vector. And I don't know if you work your solve the definition. Solve the but we need to
Okay, time's up. Anybody brainstorm want to give me a potential solution? Brainstorm. There. Brainstorm. 5 points. Minus h1. Okay. That you are thinking about doing the same trick as adding like a constant to the weights for the extra, right? Okay. Oh, I see. So you're doing 1 over. Okay. Oh, I see. Yeah. Okay. Right. So let's get back to that. You're thinking about something along those lines, but I think your solution may have an issue. It might not work because one is you're adding some constant to every edge, right? So your longest path will be. All right. So. Okay. Very good. So that's one potential solution, right? Yeah. So let's start off by thinking about this problem a little bit. I have never covered longest path before, right? You've never seen me talk about longest path. I've only talked about what? Shortest path. Okay, so we know how to do shortest path, right? So in shortest path, what was our technique? Right? Sorry, there was this thing, but forget about it. So in shortest path, what was our technique? What was the shortest path? What was the test? The test is that you look at a node and you see, do I go through it or not? Right? If I go through it and the path is shorter, I update my distance estimation. Alright, so that was shortest path, that was the idea. And it turns out that we can use a similar idea for longest path in a DAG. Alright? So what we're going to do is we modify the relaxation. Now, instead of you don't want your distance estimate to reflect your shortest path anymore. What do you want this shortest distance? What do you want your distance estimate to reflect? Longest one, not the shortest, but the longest. Okay. So I'm going to change my distance estimate such that if it's less than going to that node, I'm going to update, right, the distance estimate. If I update distance estimate, you know that I also can update the parent node, right? Do it. This is longest path relaxation, alright? And first, you initialize everything to negative infinity and then you go from there, right? So because it's a DAG, what you can do is you perform the relaxations in topological sort order. Why do you perform topological sort? Right? In topological sort order, it's simple because you know that in topological sort in a DAG, from S to some other node, you have to go through either S directly or through the predecessors in topological sort order. Right? You know that this must be the case. So you can long relax in that order. Right? So here's an example. When you do S, you relax the edges, alright? Then you get 7, 4, 3, and then I do 7, and then I relax its outgoing edges. 4, I relax its outgoing edges. 3, I relax its outgoing edges. And then 14, I relax its outgoing edges. And in the end, you will have the longest path here, 16. Okay? I'm running out of battery on my thingy. Okay, so this works because in a DAG, right, from getting from S to any other node, you kind of need to go through its predecessors, right, in topos of order. Right, so that's the idea. How long does this take? How long is it to do a topological sort?
V plus E.
Uh-oh. What algorithm do you use to do topological sorting?
DFS.
DFS. Yeah?
V plus
Alright,
E.
how long does the DFS take? B plus E, good. Okay, B plus E. And then you long relax in order. How long does that take? E, right? So, okay, so if you do that, you go back to your little special cases thing and you look in the DAG topological order that takes B plus E time. And so that you know this total time will be B plus E. Okay? So that's the longest path in the DAG. It takes 4B plus E time. Alright. There's a second solution which was given by the gentleman up there, which is you can actually negate all the edges. So you were close, but not quite. You actually can negate all the edges and run the shortest path algorithm. Alright? This works because it's a DAG. Okay? It works because it's a DAG. If it's not a DAG, this cannot work. Okay? Why? Because once you negate the edges, what happens? You can create a what? Yeah, you can create a negative cycle. And once you create a negative cycle, you know that I'm stuck, right? There's no solution. So I want to clarify something here. So far, we've been looking at finding shortest simple paths, right? In graphs. That's why we've said that okay, we're going to ignore the negative graphs with negative cycles. Okay?
Yeah, there's something.
Actually, finding the shortest or the longest simple path is actually hard. Because even though there's a negative cycle, a simple path may exist. The simple path exists. It's just that the one that doesn't use the cycle. Okay? It's just that finding it is very, very hard. Okay? So typically we just ignore the graphs which have negative weight cycles. Right? So why is this the case? It's because we kind of lose the optimal subpath property when it comes to longest paths in general graphs like this. Okay? So you can see an example here in the slides. Okay? Alright, so let's move on to the second problem, which is a bit harder. Okay, so that was the warm up. This is the harder question, which is scheduling. Right? So here's the scheduling problem. This is a real world problem that you might actually face. Okay? That given a set of tasks, let's say A, B, C, D, E, F, just an example, and a set of constraints, I want you to find a schedule. Okay? So what these constraints look like is that A must be completed at least like 10 minutes before C, B must be completed at least like 20 minutes before E, B must be done after F, right? These kind of constraints. So let's make it more concrete. I'm going to make it more concrete for you guys. Okay? So your input, guys, okay, cannot shut. Okay. The input is going to be a set of jobs and constraints. Okay, so you can imagine that this is like a task allocation. You and your friends are doing some project, and there's some jobs that you need to do, but there's some constraints. Let's say your friend must complete his task before you can start yours, that kind of thing. Okay, so let's list down the constraints. We have jobs. Let's say job. I'm going to use this instead. These are the jobs. Okay, let's say job 0. Okay, the job ID is 0. You need 1 minute to complete job 0. Okay. Job 0 must be completed before job 1, 10 minutes before job 1. Okay, so this is the interpretation. 0 takes 1 minute, must be completed 10 minutes before 1. Okay, let's look at the second one to make it more concrete. This is job number 1. It takes 5 minutes to complete. Okay, it must be completed 2 minutes before job 2, and at 0 minutes already just before job 3. Okay, so this is my input. What's my output? My output is a schedule of the earliest start times, if it is feasible to perform all the jobs and satisfy the constraints. Okay. So for example, I may want 0 start at time 0, 1 start at time 11, 3 starts at time 15, 2 starts at time 17. Right? That's a feasible schedule. Let's say. Okay. And now otherwise, if there is no feasible schedule, I want you to report on it. Okay. So let's repeat. You have an input, a set of jobs and constraints. These are for the jobs, how long they take here, and these are the constraints, right? A set of constraints. And I want you to, from this list, right? I want you to output a schedule. And the schedule is the earliest start times. So basically for job 1, I can start it at time 5, right? At job 2, I can start it at time 15, right? Things like that, all right? So I want you to output the times. So this is, when you look at this is quite hard. Where do I start? Right? I don't even know where to start. So when you have a sequence of, when you have a series of objects and relationships between objects, what is that? It's a graph. It's a graph. Your brain should go up. There's a graph.
Relationship.
Okay?
What about
The
relationship?
moment you have items and relationships between items, that's a graph. Alright. Once you have a think, your brain starts thinking graph, let's try to model this problem as a graph. Okay? Once you model the problem as a graph, start thinking about how you can solve it using one of the graph algorithms that you already know. Okay? So let me see. Let me try to get you to model the graph first. Okay? So I'll give you a few minutes. Alright? And let's see whether you can model the graph. I'll give you 3 minutes. But let me give you a starting point. You need to model two kinds of things in the graph, hopefully. One is how long things take to run. The second is these relationships or constraints. Right? You need to model these two things in the graph. So think about how you can create a graph that captures these relationships and things between constraints. Okay? So I'll give you 3 minutes and then we'll go through it.
And the distance is like, this is the time things. No,
You can work together. You work together on it, right?
The balls in the pass ID. Let's draw the balls first. You draw the balls first. Yeah, then balls. Whoa. Balls. Ball 0. It might be completed 10 minutes before 1. It must be exactly 10 minutes before 1. It's exactly or cannot be exactly 10 minutes. Must be completed 10 minutes. At least 10 minutes or soon 10 minutes. God. There's a big difference. You finish 0, right? You realize that you can do something else like 3. You don't need to do 1 to do 0.
Okay. All right. So let's think about this problem and see how we can execute it. All right. So this is a problem instance. Let's create a problem instance. I'm gonna see graphs. Okay. So let's imagine as though we create a remember when things seem very complicated, what do? We simplify the problem, make it really, really simple, right? And then we try to think it through. So imagine that, forget all the other constraints. Let's just say we have two jobs, okay? 0 and 1. All right? Imagine that 0 takes 0 time to complete. Let's just say it's instantaneous. Let's just say, make it very simple, right? It's instantaneous. And, but it needs to be completed before job 1 and 10 minutes. Okay? Job 1 also takes 0 time and doesn't have any constraints. Let's just say, this is already very simple. I cannot make it much simpler than this, right? So let's think about this very, very simple situation. So if you want to figure out the earliest start times, right, what do I need to do? What kind of graph I help me here? So you know that job 0 and job 1, there should be some dependency, right? So here, what we're going to do is we can say, okay, you know what? Why don't we try this? We're going to say job 1, right, must be executed 10 minutes after job 0. Okay, instead of job 0 being executed 10 minutes before, there must be this constraint is represented by an edge weight. Alright, so there we go. 0 must be executed 10 minutes before job 1, right, in this particular situation. Right, if it takes 0 amount of time. Alright. So we can extend this idea to more complicated setting. Let me take it a step at a time first. Okay, let's not jump there. Okay, so now let's say job 0 takes 5 minutes to complete. Let's say job 0 takes 5 minutes to complete. So 0, 5, and then you need to execute it 10 minutes before job 1. Alright? So what I'm going to do is I'm going to split up job 0 into 2 nodes. Okay? This is going to be the start of job 0, and this is going to be the completion of node 0. There's going to be one edge between them, which says this will take 5 minutes long. Okay? And the completion then goes to 1. This is 10 minutes. This is my constraint. Okay? So that means that if this is the case, if I sum up the weights here, 5 plus 10, I know that I can only start job 1 after 15 minutes. Right? I need to know how long I need to sum 5 plus 10, right? And this is 15 minutes. The earliest I can start job 1 is 15 minutes. If I start job 0 at time 0, right? If I start job 0 at time 0. Okay, close. Okay, so that's my setup. Okay, that's my setup. Now I'm going to generalize it to the more complicated case. Alright? So what I'm going to do is I'm going to repeat this process again and again. Alright? Where I'm going to expand out every node into 2 parts. Alright? So in this case, I will also expand out okay, and if it's 0, it doesn't take any time to put 0. Okay? So that's going to be how I'm going to construct my nodes and the relationships between the nodes, the edges. So again, let's repeat. You have some start, some completion, some execution time, and your constraint. Okay, and you do this for each of the nodes, each of the jobs in your constraint list. Okay, you need 2 other nodes. Why? Because you need to find from one node to all the rest, effectively, right? So you need a dummy start node, okay, and you need a dummy end node as well, right? So you're going to start with the dummy end start node, right? You're going to start this is going to be your fictional source, okay? Because it's not necessarily the case that you start with S0. It's not the case that you might start with S0. Okay, S0 might have some constraints of its own, right? So you may not start with S0, so you need some dummy node, right? The dummy node is just some fake job that is connected to all the other nodes in the graph, right? So that's going to be your dummy node. We want the earliest start time for each job that satisfies the constraints. The earliest start time, not the latest, okay, the earliest. So if I want the earliest start time, what can I do? This looks a bit like a path problem, right? Because what I want to do is like find the earliest start job. Remember, we were looking at the paths, and what were we looking at? What were we doing? We were summing up the distances along the path, right? Is it the shortest path that we want? Do we want the shortest path? So if you take the shortest path here, let's say you took this example, you write, I want to know for S2, let's say. What's the shortest path from S0, let's say? The shortest path is this one, right? This one. But remember, you cannot start job 2 at time 1, right? Because you won't have time to finish these jobs. Remember, these jobs are the constraints, right? You have to finish them before you start on S2. Okay, your friend must finish their job before you can start putting the last pieces of the code together, right? So you cannot start your job first, right? So shortest path is out. You cannot use shortest path.
Minimum spanning
What
tree.
can you use if you cannot use? In this case, it's not shortest path. What is it? What is it that you want actually?
Minimum spanning tree.
You want the longest path. It's not the shortest path, it's the longest path, which we just did a while ago, right? You know how to complete longest path, at least in a DAG, right? Okay, so how to find longest path? So, what are the two techniques we learned to find longest path? Okay, the simplest one is you negate all the edges, right? And then we run the shortest path algorithm. In this case, we have negative edges and we're not sure what it is. It might be a DAG, it may not be a DAG, right? So if it's, we negate all the edges, and then if we negate all the edges, what algorithm can we run? What algorithm? Can we run Dijkstra?
No.
No, we cannot run Dijkstra. Dijkstra doesn't allow you, it doesn't work for negative edges. What works on negative edges? Bellman-Ford. Good. So you run Bellman-Ford. Okay? When you run Bellman-Ford, Bellman-Ford tells you the shortest paths. Okay? You start with from the dummy node. Okay? So the shortest path, right, with the negative edges will guarantee that the constraints are met, right? Because you're running Bellman-Ford, if it takes more than minus v, if you're running for v cycles, v iterations, and you notice a change, that means that negative cycles exist. No feasible schedule. No feasible schedule. Okay? Then you return null. If actually, if you're guaranteed that the constraints form a DAG, then you can use topological sort, just like the one we did before, right? But in this case, we weren't guaranteed that this necessarily is a DAG. Okay? So that's it. That's the algorithm. Okay? Very simple. Once you construct the graph, the trick, of course, the difficulty was constructing the graph. Once you construct the graph, then the algorithm itself is something that you know already. You can just run Bellman-Ford, right? And that tells you what the answer is. Okay? All right. So, any questions about this particular problem? Wow, okay. There's a lot of questions suddenly. Okay, let me take it one by one. Okay, so let's stick with why E log V is bigger than V log V. So can anyone tell me this? Why is E log V bigger than V log V? So in the worst case, E is V squared, right? That's not nice. In our case, actually, the graph is guaranteed to be connected, right? So at least you will have how many edges? V minus 1 edges, right? So in the same order of V, all right? So you don't have to worry about it. That's why we use E log V, okay? Say quiz 3, okay. And as in the beginning of the lecture, quiz 3 will be next week on Wednesday, all right? On Wednesday. Don't come on Tuesday expecting a quiz. It's on Wednesday. Okay? Come on time, please, because we want to give you as much time as possible. Okay. This here. I think that's fine. Oh, how many E log V's? Or a lot of E log V questions. Okay. So maybe I'll go back and explain it again. So let's go back and look at E log V. Okay, so let's look at the algorithm one more time. I think an example will help. So remember what are the steps of our algorithm, all right? In our algorithm, we add a node, right? We add a node, the weight is 0, okay, we take it out, that's going to be now S, and then we look at its incident edges, okay? Once we look at the incident edges, we're just going to add the respective node on the other side of the edge, all right, to our priority queue, okay? And the priority queue will tell us which one is of minimum weight, right? Okay. Once that's of minimum weight, we take that out, okay? And then we look at G's incident edges, okay? When we look at G's incident edges, what can happen? We may find a shorter way, a smaller edge to one of the other nodes, okay? So in this case, we're going to see that there is actually a shorter edge here, a lighter edge to E, right? So E was formerly 16, but remember we want the lightest edge, right? So we're going to update the value for E to be 6 instead of 16, right? Corresponding to this edge, all right? And the same for H as well. So what is this operation? This operation is, we only do this when there is a lower estimate, right? So, a lower edge value, edge weight. So this is a decreased key, right? This is the decrease key operation that we've seen before, right? So we decrease the key. In decrease key, this takes log v time, because at worst, this will have v nodes, right? So it will take log v time. Now, how many times do we do this decrease key operation? Now, at worst, you will, every time you up at the node, right? Every time you're looking at the edges. Worst case scenario, every time you look at an edge, you're going to decrease. Okay, so that's going to be E log V time. All right, so that's why it's E log V time. All right. Okay. Can we alter relaxation algo and use Dijkstra? For the longest path in a DAG, you can, but it's not optimal, right? You can do it a bit faster if you use the topological sort method. Okay. Why is it a longest path problem? For the scheduling, you mean, I think, right? So for the scheduling, it's the longest path problem because we want the earliest start time subject to the constraints, right? And the constraints, remember how we set up the constraints? The constraints were set up. So let's look at this very simple example because okay, so let's look at this very simple example because I think that tells you why you want the earliest time and not the why you want the longest path, right? So if you have this set up, right? Imagine that each of the jobs doesn't take any time. Okay, so if the longest path from 0 to 1 is via this, right? So imagine if you had another constraint, right? Which says that it takes 0 time after. It takes 0 minutes. Let's just say I'm just making this up now. Okay, we have a hypergraph, but it's okay. Imagine if you had this constraint, right? Now, for this to be a valid schedule, all the constraints must be satisfied, right? Now, if you take the shortest path, you will follow this edge, right? Which is not correct because you won't satisfy all the constraints, all right? You need to satisfy all the constraints, which is this 10 minutes over here. So, likewise, when we have a more complicated setup like here, right? You want the longest path because essentially you need to satisfy all the constraints before you can execute S2. Right? So you can think of this as dependencies. So you guys install Git and all that, right? When you install a new software. I mean, you can't just install software, usually it has dependencies that you can install first, right? Likewise here, what we're doing is we have like a dependency graph, okay, or constraint graph. Alright, so before you can execute S2, you actually need to execute C1 first, job 1 first, and job 0 first, because there are these constraints over here. Alright, and then you need to satisfy these constraints. Now, to find the time to which you need to satisfy these constraints, you don't look at the one that is the quickest. You look at the one that takes the longest, right? So, for example, let's make it very, very concrete. You're doing a project. You have 2 friends. Your task is the last one. You need to take they're both writing 1 paragraph of some report, and your job is to combine the 2 paragraphs together. Let's say, okay? The first guy takes 1 minute to do it. He's very fast, very efficient, awesome lab partner. The other one is a lazy ass, takes you 2 days to finish, okay? So, can you start your job 1 minute after? You cannot, right? You have to wait for the second guy, the lazy ass, to finish first. So you need to wait 2 days. Okay, so this is why we want the longest path. We cannot do the shortest path here, alright? We want to satisfy all the constraints. Can you use a maxi for? Oh yeah, you can also do that. This is more difficult. Why is it more difficult? It's because you can have multiple constraints on the same job. Alright? Then you can add it to all the other constraints, which is more difficult. Why is it longest path on DFS? Because in this case it's a weighted problem, right? Each of the edges take a different amount of time. So the scheduling problem can't be used to modify the Dijkstra since there are no negative edges. For one thing, you have to be guaranteed that there are no negative cycles. and that's not the case here, right? If you use the negative trick, negative A to H trick, so you make every positive edge into a negative way, then you actually you can't use the extra directly. Okay? So you can try it with positive cycles. You can try it with the modified vector. Yes, actually. So, finding the shortest path in a graph, if you're guaranteed no negative cycles, I guarantee you no negative cycles, it's not NP-hard. Okay? But in an arbitrary graph, it's NP-hard. Right? Oh, what's NP-hard? Okay, that one wait for 3230, but essentially it's a class of complexity. Okay, the polynomial time, you have non-deterministic polynomial acceptable NP-hard. Don't worry so much. It just means just take it as very hard. Okay, very, very difficult. Cannot solve quickly. Okay? There is no NP easy.
Oh, what I do?
There is no lecture tomorrow. Okay, quiz on Wednesday. Quiz 3 is on Wednesday next week. I said this already. Okay? Alright. Okay, so I don't know why this thing keeps Alright. Okay, we're done for today. There is lecture next Tuesday, so don't skip lecture next Tuesday. There's lecture next Tuesday. We'll cover two styles and uniform. Alright, don't skip lecture. Okay, see you next Tuesday.